So today I'm going to talk about another topic, also in the framework of storage, but now it's going to be specifically about hydrogen. So I'm going to talk about experience specifically in Germany, and therefore I'm going to start with an introduction of the energy transition that yesterday I already introduced to you, and then some routes for generation of hydrogen, state of the art of the technology, projects, legislation, efficiency, and so on. So yesterday we talked already about Energiewende, or energy transition in Germany, and we said that is the effort of the federal government of Germany to establish targets for integration of renewable energies, phase out of nuclear power, increase of efficiency, and expansion of the grid network. So in this slide I'm going to show how the trend has been. This is from 2008 and a perspective to 2050. And the two main trends is that all the fossil fuels are going to decrease and all the renewables are going to increase, up to the point that in 2050, 80% of the energy matrix is going to be based on renewables, which is a very ambitious target of Germany. It is also interesting to note the role of fossil fuels in the future. We were talking about it now in the morning in the taxi with the colleagues from Duke University. There are different scenarios and different perspectives of how it is going to be with fossil fuels. Because, for example, I'm going to talk about the case of lignite. In the east of Germany, there are very wide reserves of lignite. And it represents now 25% of the energy matrix in Germany. Nevertheless, there is a discussion if the plants are going to go on cold reserve or in warm reserve as a spinning reserve. And different scenarios, for example, say that coal is going to be the energy bridge before the renewables come. Of course, before that, it would be necessary to do a process of flexibilization of the power plants to be more easily dispatchable. And some others say that coal is going to disappear by 2030. So these specific policies are still to be defined. The only ones that are written on stone, so to say, is that nuclear power is going to be decommissioned by 2022. That yesterday we already said is 13% of the energy matrix. And that renewables have feed-in priority regardless of the situation of the grid. These slides are showing different scenarios. And for example, you see how it's going to be. Here is 2030. This is the part of fossil fuels, and these are the parts of renewables. And we are seeing that they are going to grow and grow. And at a certain point, all these parts are going to be necessary to be stored. Yeah, the red line is showing the demand, and this all is going to be the overcapacity. And as you can see, 1, 2, 3 is around 40,000 megawatts. That it's in theory going to be the storage capacity for Germany. And that's why the efforts already started to be a priority of the federal government. Given this situation and this time pressure, there is absolutely necessary to do investment in research and development of fast reactive storage solution, like batteries that are used mainly for the primary reserve, able to supply energy in milliseconds. But it is also necessary to count on storage technologies that are going to be for long term. And in this case, hydrogen is a promising technology because you don't have any losses. You can store it even for seasons. And that is what happened in Germany. For example, you will produce much more solar power in summer, and you can store it for months until you can use it in winter. So that's why hydrogen is a focus on the German policy. Hydrogen also had the advantage that you can do this sector coupling. You can produce electricity, you can produce heating, and you can even use it in the transportation industry. And that's why this makes it a very versatile energy carrier. Furthermore, that is only for the energy sector, electricity, heating, transport. Also, hydrogen has using for chemical industry. It is a raw material for the production of steel, for glass. It is used for different chemicals. It can produce methanol from it. And if a process of methanization is carried out with CO2, then you can also use the methane as a much more compatible energy carrier with the system. For example, attaining the same characteristic of biogas or natural gas. This is just a slide showing some of the advantages of hydrogen in the transportation industry. In this case, if we are talking about biofuels, liquid biofuels, like biodiesel from rapeseed or ethanol from sugarcane, like in the case in Brazil, we are always talking about a fuel that is carbon emission neutral, because all the carbon emissions are going to be absorbed by the crops while growing, and then they're going to be released to the atmosphere. In this case, hydrogen could have even a negative CO2 stock, because if you generate hydrogen with electrolysis, but then you find a cheap source from CO2 and you mix hydrogen with CO2, then you're actually taking it from the system to use it in a fuel. And when you burn hydrogen, then of course the process is the reverse of electrolysis, and then a car driven with hydrogen in the exhaust gas, instead of having a polluting gas, is going to have water. So talking about the technology, there are 3 technologies that are paying more attention: the alkaline electrolysis, PEM electrolysis, and high temperature electrolysis. The high temperature is more in the research and development stage. The alkaline electrolysis is the one that is consolidated since very longer time. And the PEM is a proton exchange membrane. It is now in the market as well, and it is commercialized in Germany. It's also comparably competitive prices with the alkaline. Nevertheless, the alkaline electrolysis process has been already in the market for a longer time. We know the degradation processes. They are plants running for a very long time. It's not the case of the PEM. Right now, there is no a plant in Germany running more than 10 years. So also the aging mechanisms of the key components like the stack is not known. So there is still the doubts of what system is going to be better at the end. Is still a discussion. There are a lot of people arguing that alkaline is going to be in the future a technology. Also, there are another group of people that say that the PEM is going to have a better discussion. Right now, there are no concrete answer. It is also going to depend on the application and what the priorities is. The big advantage of PEM is that you have a smaller size in the stack, and it's a more compact technology. So if you have restrictions of space, then you can use the PEM. But if you don't have restrictions right now, the alkaline is slightly cheaper as well, and there is more experience with it. So it is always this question of which technology to implement, and it is an open question still. Here in this slide, you're going to see some advantages and disadvantages. As we said, the alkaline is more mature, but the PEM has a higher density of current. And right now, the costs are still more expensive for PEM. But for example, companies that are installed in Europe, they are trying to level both prices so that the PEM enter in the market. And this has been an effort. There are not so many companies working with electrolysis technology and fuel cells. We have, for example, Hydrogenics from Canada, McPhee that is from France, and I think all of you in this room should be very proud because there is one company in Brazil called Hydron that it is producing electrolyzers, and hopefully it's going to also become a world player, and we have a presentation with them later in this event. One of the advantages of PEM as well is the flexibilization. You can have a minimal load of 2% and an overload of 300% compared to the alkaline. These lines indicate that this is a result obtained by the industry, and these results are obtained in laboratory scale at our university. So as I said, the decision of implementing one or other solution will depend specifically of the operation mode and the requirements of a system. The good thing of hydrogen is that similar to batteries, it is a modular technology, and you can actually make arrangement of smaller sizes in order to create a large system. This, for example, is a system from McPhee using a 2 megawatt electrolyzer, and if you do the arrangement, you can do a plant of 10 megawatt with a proven technology in sizes. These are also some slides about the costs, and the stack is the most expensive component. For an electrolysis plant, you also have some auxiliaries, and in the case of alkaline, you need another kind of gas cleaning technology because you have to remove the KOH is potassium hydroxide. But in both cases, the stack is going to be the most expensive component. What it is very interesting about the hydrogen technology is that it is not a new technology. Already Julio Verne 100 years ago was thinking that in the future all the cars were going to be running with water, and they have ideas of fueling boats with water, and the idea of just separating hydrogen and oxygen through electricity is it's a technology already existing. It's now that is coming back in large scale. In Germany, we have different pilot and demonstration plants. Here it's ours in the east of Germany, in Cottbus. We have an alkaline hydrogen plant. We will show later, but there are different projects that I'm going to talk about some in the next slides. This is our university, and this is our hydrogen research center. This is a hydrogen tank that we have there. And we have one small electrolyzer for hybrid plant that we have on the roof of our faculty. And we have a small electrolyzer with solid storage in metal hydride. We also have a large-scale electrolyzer that is alkaline technology, but it's a pressurized technology, meaning that you don't need compressor after doing the electrolysis. This is one very important example for Germany because it's the only one with pressurized alkaline electrolysis in the country. This is our system. Yesterday there was a presentation with, I think it was the second presentation yesterday, with a similar project. And this is how it looks like. We can get, in our building in the university, we can get electricity from the grid, or we can get electricity from solar panels or solar collectors and a small wind turbine that is designed for urban areas. If we have a surplus, we can store it either in batteries, or we can use an electrolyzer and store it in small bottles like this size for metal hydride, and then we do the reconversion with a small fuel cell. And we can either sell it to the grid or use it in the university for normal electricity. So there are many examples like that in Germany, small scale or industrial scale. This, for example, the project VESPE is a storage of wind energy in large scale, and there is also a lot of research for geological storage. So instead of storing the hydrogen in large tanks for compressed gas, there is also the possibility to store it in aquifers, depleted gas fields, or salt caverns. The idea, of course, is that once the offshore wind industry in Germany spreads, it's going to be on the north coast of Germany. And there is the possibility to build salt caverns, which would be able to store in large amount the hydrogen. And now, of course, the problem is going to be how to transport all the electricity to the south, to Munich, to Stuttgart, where is the main focus of consumption, that is the automotive industry. For that, of course, is the development of ideas for direct current, high voltage grids to have the less losses possible. But this project is studying all these aspects for storing wind in large scale. This is another project in the airport of the city of Berlin. And they are storing the hydrogen in solid, in metal hydride, because they need extra security when it is an airport, when there is also a lot of kerosene. Thank you. A lot of kerosene, and you have to reduce all the risks, maximize security. But this is an electrolyzer for McPhee that is already commissioned since 2014. There are other large-scale projects. This is in one that our university is also participating. That was, here's the inauguration with the Chancellor of Germany. And it is a project in the area of the Uckermark. And this project is also this... okay, this hybrid power plant shown here is this one. So the idea of the plant, you have different wind turbines. It's the 3 different plants. When you generate electricity, you can either sell it to the Sistema Interligado Nacional, you can sell it to the grid, or if you have a surplus and you are unable to inject it in the grid, then you can run the electrolyzer and store it in tanks. There is a fuel station there for charging trucks or cars with hydrogen, or also you have the possibility to inject it in the natural gas grid. This technology is called power to gas. And according to German legislation, right now you can inject up to 2% in terms of volume with natural gas. Yeah. The other possibility would do to do methanization, and then there is no restriction because of the characteristic similarity with natural gas and biogas. In this case, in the plant from Uckermark, they generate the hydrogen, and they also have a plant from biogas, and both of them go to the natural gas grid, where a combined heat and power plant produce electricity and heating in the way of district heating from a close-by city. So these kind of integrated plants are already a reality in Germany. And right now the discussions are more oriented in how the legislation is going to evolve. Because the 2% legislation is mostly based on the oldest technologies. Germany has already experience of pipes running 100% with hydrogen in all the sector of the chemical industry, the area that is called in Germany Leuna. And they already have built pipes where hydrogen is transported, and there is no fragilization of the material. For this kind of transition, then it is necessary to do an inventory of the pipes for natural gas and to evaluate if the material is going to stand a higher percentage of hydrogen mixed with the natural gas. This is another park that is located in Mainz, and this has an PEM electrolyzer, and it is also doing power to gas. It's also injecting in the gas pipe. And this project is very iconic in Germany. It's a project by Audi, and it is a project that has methanization. It's the biggest project in Germany doing methanization. And then hydrogen is generated and mixed with CO2. The problem in Germany for that is the availability of CO2. Because to obtain it from the air is very expensive, and to do CO2 capture and storage will depend on the nearby location from a source. And in this moment, it's still in experimental because right now the CO2 is very expensive. Nevertheless, the Audi has proven to do a good job in this work, and it is a very representative example of the trend of the technology. All these projects of power to gas have been supported by the government and especially by the German Energy Agency because of the suitability for it. In Germany, the electricity grid and the gas grid are very dense, so it is located very, very close to each other, and you have the possibility to locate the electrolysis plant and to decide if you are going to produce electricity in the moment or if you are going to inject in the natural gas, and you have this flexibility. In Brazil, there is also this condition, for example, in the part of Sao Paulo, where you have the Sistema Interligado Nacional with a very close proximity from the gas pipe that comes from Bolivia. So one of the options for Brazil to reduce the dependency on imported gas from Bolivia would be to reduce their consumption by introducing hydrogen. This, of course, will require a lot of legislation work because right now in Brazil there is no anything like that. Nevertheless, in some talks we had with ANP, we knew about the process, how it happened with the natural gas, that samples have to be obtained and you have to decide who is going to be the customer. And you have to evaluate the technology, the infrastructure of that area, if the material is going to be fragilized with hydrogen. But after doing all the certification process, in theory, it would be possible to insert this new technology in the Brazilian energy matrix. In Germany, we have different possibilities for storage underground. And as I said, aquifers, depleted natural gas fields, or salt caverns that are man-made. And then you only need the brine solution, and then you can actually design your reservoirs depending on your needs. In this case, it would be necessary, if such technology would be implemented in Brazil, it would be necessary to investigate which geological areas would be suitable for such storage. But for example, for areas like the Amazons, where there is very limited possibilities to extend the grid, there is also the possibility to generate hydrogen with some surplus renewable energy and replace the diesel that is used in these locations that are isolated from the grid. And gas turbines or gas motors are also a solution for reconversion. So as I said, hydrogen is very versatile, and there is a lot of work to be done to implement it in a country like Brazil, but it is already a reality in Germany. Also very positive is that the costs have been decreasing in the last years, and also the costs are going to reduce depending on the size. The larger the size, the lowest is going to be the investment necessary. And when we are talking about the operation costs, you are going to receive these slides, and then you can see it in more detail. But we have worked with some scenarios from the present and for the future. And all our studies point out that the cost of electricity is going to be the main factor, is even more important than the cost of investment. In Germany, it makes sense because we have an overcapacity of renewable energy, and there are no possibilities to inject it on the grid at all times. So all this surplus electricity, that is waste electricity, that some years ago the people preferred to turn off the wind parks just to flip the turbine up to stop injecting in the grid, that electricity is perfect to generate the electricity necessary for an electrolyzer to generate the hydrogen. Talking about the efficiency of conversion, all these chains are going to have different efficiency depending on the arrangements. You usually have a source of renewable energy, you need a transformer and a rectifier, and then you have an electrolyzer. And for example, this chain is showing how the efficiency would be if you transport the hydrogen in a truck. For that, you need a compressor, and you are going to lose efficiency in each of the steps. But if you use the highest technology with the best efficiency, in theory, you should be obtaining 78% of efficiency from the electricity that you are generated. Now, this efficiency level is relative because if you do a pipe transportation, either with natural gas or with only hydrogen, then the efficiency is going to change. If you have storage in caverns, then when you inject the hydrogen, when you remove the hydrogen, you have losses, so this is going to change. And finally, for the reconversion, if you use a gas turbine, a hybrid plant, a fuel cell, all these efficiencies are going to depend exactly on which component you are choosing for the arrangement. But in the slides, you are going to have more opportunity to see how the state of the art for technology in Germany is having different efficiencies, and at least to see why Germany is so supported and it has become a priority. To conclude, I can say that there is still a lot of improvement areas as well. There are different topics for research and development, for optimization of the stack, for the distance between the plates, for the diameter of the bubbles of the electrolysis process. So it is still a technology that can be enhanced, and the government of Germany set a lot of funds for research of the technology itself, for the legislation, and for the conversion cells as well. So thank you for your attention, and we can discuss after the first session is finished. Thank you.
Muito obrigado, doutora Cínthia. Vamos então de imediato passar à seguinte apresentação.